My name is Karen Daly and I teach mathematics at DKIT, a third level college in Ireland. This video was produced to further assist my first year computing students with their mathematical studies. At the end of this tutorial, you should have an understanding of the fundamentals of logic. Beneath this video, you'll find a link to a Word file which has a copy of the question I am answering in this video. I would suggest that if you can, you should pause the video and print this file out and have it in front of you as you watch the video. Enjoy! Let's look at a typical logic problem. Part A. Say, giving a reason for your answer, whether each of the following is a valid or invalid argument. Part 1. Here you're given two propositions. The first one is, all computing students enjoy programming in C. The second proposition, Anne enjoys programming in C. And what you're asked to do is say whether the conclusion, therefore Anne is a computing student, forms a valid or an invalid argument. This argument turns out to be invalid. So why? Let's consider a little diagrammatic representation of this problem. Here we have a box, and this box represents all the people who enjoy programming in C. Now, the first statement says that all computing students enjoy programming in C. So we have a little circle here that represents all computing students. All right. Second statement says Anne enjoys programming in C. Now Anne certainly could be part of this all computing students set, but also Anne could be out here. Anne could form a little point just out here outside that set, and it would still be true that Anne would enjoy programming in C. So for that reason, this argument here is invalid. Now if we look at part 2, the argument reads, Dundalk is in County Cork, Anne lives in Dundalk, therefore Anne lives in County Cork. This particular argument turns out to be a valid argument. Again, if I was to explain why, it probably is easiest by looking at, again, a diagram that would represent this. Here again I have a box, and this box here actually represents County Cork. Inside County Cork is Dundalk, so again I'll give it a circle and I'll call it Dundalk. So Dundalk is within County Cork. That's the first proposition. The second proposition says Anne lives in Dundalk. So Anne again is inside this box. Right? And if Anne is inside this box, which is Dundalk, and Dundalk is a circle that is within County Cork, then the conclusion Anne lives in County Cork is a valid argument. A couple of things to remember. Firstly, as in part 1, to show an argument is invalid, all we have to do is demonstrate one exception where it does not hold. The second thing to remember is that for an argument to be valid or invalid has nothing to do with the propositions being true or false. Let's move on to part B of the question. Here I'm given three propositions, P, Q and R. And what I'm asked to do is express the following logic statements in English. Before I begin, let me recall for you the logic connectives and their associated English. So if we write out the solution, what we'll get is Q, I will go skiing at Christmas. Now again, if we look at our table and look for the logical connective, it's a V, and the V represents the word or. Or is Man United will win the league. And that's the answer to to part 1. Now let's look at the answer to part 2. P is the proposition. I will go to New York during the summer holidays. During the summer holidays. Excuse the writing. Now if you look at the connective next and read it from the table, that's the and connective, so I write down the English and. The next connective is the not symbol, and it's in front of Q, and Q is the proposition I will go skiing at Christmas. So not Q is the proposition I will not go skiing at Christmas. So I'll write that down, and I will not go skiing at Christmas. And that's the solution to part 2. Now if we look at the solution for part 3, or with an arrow pointing towards P stands in English for if, or, then, P. And if I was to write out then all the English that's associated with proposition or and P, I would get the solution being, if Man United will win the league, then I will go to New York during the summer holidays. For part 4, this symbol here stands for the if and only if symbol, along with the not symbol. So if I was to write it, it would be P, if and only if, not Q. And putting in the English, what I would get is, the solution reads, I will go to New York during the summer holidays if and only if I will not go skiing at Christmas. And the solution to part 5 of the question will read, not or, and this is the exclusive or, Q, so it's going to read either, not or Q. So the either or is the symbol here. And the solution will read, either Man United will not win the league or I will go skiing at Christmas. Now if we move on to part C of the problem. Part C of the problem asks us to state in English and in logic notation the converse and the contrapositive of this statement here, or implies not P. Now let's try part C. Here we're asked to state in English and in logic notation the converse and the contrapositive of this proposition. If, or, then, not P. The converse of this proposition is just the proposition written the other way around. So it's going to be not P implies or. Or written in English, it'll be if not P, then or. And filling out all the English we get, if I will not go to New York during the summer holidays, then Man United will win the league. The contrapositive of this statement is going to be not P implies not or. When there's two nots coming together, they'll cancel each other out. So that's the same thing as P implies not or. And if I was to write that in English, it would read, if P, then not or. Or filling out the full English form, I will get, if I will go to New York during the summer holidays, then Man United will not win the league. So this is the answer in logic notation, and this here is the answer in English. So to answer this question in an exam situation, you will need to know the definitions for converse and contrapositive. Now for part D of the question, we're asked to write down the logic expressions for each of the following. Now the first one is either I will go to New York during the summer holidays, or I will go skiing at Christmas. Now that's the symbol plus with a circle around it that I introduced earlier. I will go to New York during the summer holidays. That's proposition P. I will go skiing at Christmas is proposition Q. So that's the answer. Now for the next part, the sentence reads, I will not, so I'll highlight not, go skiing at Christmas if and only if Man United will win the league. Now the not symbol is this symbol here, which we introduced earlier. And the if and only if symbol is this symbol here, which again I introduced earlier. So it says, I will not go skiing at Christmas. I will go skiing at Christmas is proposition Q. So it's going to be not Q. If and only if Man United will win the league is proposition R. So there's the solution. So for part 3, we have the sentence Man United will not, I'll underline not, win the league, but I will go to New York during the summer holidays. Now the but in this question is the same thing as saying and. So it's going to be the logical connective and. So if I write these down, what I get is the not connective is this connective here. The and connective is this one here. So it's not, Man United will not win the league. Man United will win the league is proposition R. So it's not R. And I will go to New York in the summer holidays is proposition P. So it's not R and P. And that's the solution. Now let's move on and do part E of the question. You're asked to set up a truth table for the logical expression, this here, stating whether this proposition is a contradiction, a tautology, or neither. Now the first thing you do is look at the logical expression and identify how many different propositions there are. So here we have a P and R and a Q within the logical expression. So down here on the table, I'm going to have a column for P, I'm going to have a column for Q, and I'm going to have a column for R. Now when I have that done, what I need to do next is break the logical expression down into pieces and do each piece separately in the table. So again, if I identify this from the equation, I've got P exclusive R that I will have to do. So I'll put in a column for that. The next one is I'll have to do not Q. Once I've done not Q, then I can do not Q and R. And lastly then, I will do the entire expression. So hopefully I can fit this in. P exclusive RQ implies not Q and R. So I'll put a bracket around these two pieces. Now I fill out the table. P, Q and R form the input to the table. So I write out all the combinations of zeros and ones or false and trues that I can possibly have for P, Q and R. So I'll begin with the first one as being 0, 0, 0. The next one 0, 0, 1. The next one 0, 1, 0. The next one 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. That's the same thing as counting between 0 and 7 in binary. To fill out the rest of the table, I have to know the truth tables for each of the logical connectives. For this logical connective here, it's the exclusive OR. And I'm putting that between these two columns here. All right. Exclusive OR is false for 0, 0 and also for 1, 1. So it's false in this case. The next one is 0, 1, so it's true. 0, 0, it's false here. 0, 1, it's true here. 1, 0, it's true here. Now 1, 1, it's false for. 1, 0, it's true for. And lastly 1, 1, it's false for. Now the next column is the not Q column. So what I do is I go to the Q column here and I look at the values, and wherever there's a 0 I write 1, and wherever there's a 1 I write 0. So 1 I write 0, and then 1, 1, and 0, 0. Now for the next column, this here is the AND symbol, right? And I'm combining this column here with this column here to get this column here using this AND symbol, right? So if I highlight the first entry, well, firstly, AND is only true when I have a 1, 1 input. Here I've got a 0, 1, so it's false. So AND is only true for a 1, 1 input, and here I have a 1 and a 1, so this is true. 0, 0, false, 1, 0, false, 0, 1, false, 1, 1 again. Here's a 1, 1 input, so it's true. 0, 0, false, 1, 0, false. Now let me do the final column. To do the final column, I have to take this column here and this column here, and I have to combine the two of them with an implies sign. So I'm doing it in a different color, so hopefully I can see this. So I'm taking them two, and I'm getting this by putting the implies sign in between them. Now, implies is only false in one case, when I have an input of 1, 0. So this first value is here, I have 0, 0, so it's true. This one here, I have 1, 1, so it's true also. This one here, 0, 0, true. Now here's one. I've got a 1, 0 as the input, so this is actually false. 1, 0, again, false. 0, 1, true. 1, 0, again, false. And lastly, 0, 0, true. So this gives you the truth table for the logical expression. Now what you're also asked is the proposition a contradiction, a tautology, or neither? To get the answer to this question, we look at the last column. For the proposition to be a contradiction, the last column would contain nothing but zeros, would be entirely false. And as you can see here, if you look at the last column, it has a mixture of ones and zeros. If the expression was to be a tautology, then the last column should have nothing but ones. It should be entirely true. And again, if you look at it, it's a combination of zeros and ones, so it's not a tautology. So the answer to this question is that this particular logical expression is neither a contradiction or, let me move this up a little bit, a tautology. So remember, to do this question, firstly, you need to know your logical connectives, and secondly, you need to know their associated truth tables. And then thirdly, to do the very last part of this question, you need to know the definition of contradiction and tautology. So let me summarize what we need to know. The English not in logic represents this symbol here. And to generate the truth table for the not symbol, you change 1 to 0 and 0 to 1. The English and in logic is represented by this symbol here. And to generate the truth table for AND, remember that AND is true only for the input 1, 1. The next symbol in English represents OR. It's called the inclusive OR, and it has this symbol here. To generate the truth table for OR, what you need to remember is that OR is false only for input 0, 0. The next one is either or, and the symbol for that is this here. And to generate the truth table, what you have to remember is that either or is false for two inputs, 0, 0, just like the inclusive or, but it's also false for 1, 1. For either or is the exclusive or, so it's A or B, but not both. The next one is if then. This has this symbol here, and again, to generate the truth table, what you need to remember is that it's false only for the input 1, 0. And lastly is the if and only if, which has this symbol here. And what you need to remember is that to generate this truth table, it's false for two inputs, 1, 0 and 0, 1. Let's look at part F. We're asked to prove or disprove this particular logic statement here. The first thing to note is this symbol here. And what that stands for in logic is logically equivalent. I-V-A-L-E-N-T. Now you have two sides of this statement. You have this side here, which I'm underlining, and this side here. And you're asked to prove, are they logically equivalent? To do this, we produce the truth table for both sides of the statement, and we look at the last column and we see, are they identical or not? Now let me take the left-hand side of the equation and produce the truth table for this. First thing to note, as we said before, is the number of different propositions in the statement, and in this case there are three. They're called P, Q and R. After that then, what I'm going to do is I'm going to break the statement down into its individual parts and then build it up to show you the truth table for the final column. So the first part is Q implies R. We're going to have a column for that. The next part is not P. We're going to have a column for that. And then lastly, we have a column for the entire statement. Q implies R, exclusive R, not P. Sorry, it's a little bit squashed. Now there are 8 initial states for P, Q and R, and they are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and lastly 1, 1, 1. Now filling out the if Q then or column, what I do is I recall firstly how to produce this logic table, and this logic table is false only in one case, and that case, I'll underline the first instance of it, is when you have a 1 as the Q value and a 0 as the R value. So it's false here. It's true everywhere else. So the only other instance of that is 1, 0 here, it's false here. Everywhere else then it's true. So you've got a 1, a 1, a 1, a 1, a 1, and a 1. The column not P is an easy enough column to fill out. Wherever there's a 0 in the P column, I write a 1 in the not P column. So I've got 4 1s. And whenever there's a 1 in the P column, I write a 0. So I've got 4 zeros. Now let me change colour to fill out the final column. What I'm asked to do is I'm asked to combine this column with this column using the exclusive OR symbol. Now recall the exclusive OR symbol, the truth table for that is, it is false in two cases. The first case is where you have a 1, 1 input. It's false there. So there's another one of them. There's another one here. And the other case that it's false for is in case of 0, 0 input. So it's false there also. Everywhere else it's true. So I'm going to put in 1s everywhere else. Now there's the final column for the truth table for the left-hand side of this logic expression. Now let me generate the truth table for the right-hand side of this logical expression. Again, we have 3 different propositions, and they are, as before, P, Q and R. So I'm going to write these down, P, Q and R. Now, again, building it up in piecewise, we're going to have a column for not R. We're going to have a column for P, R, Q. And then we're going to have a column for not P, R, Q. And then lastly, we're going to have a column for the entire lot, which is not R, if and only if, not P, R, Q. Okay, let me move the screen up a little bit and let's fill in the truth table here. Sorry, that should have read Q. That's a Q. Okay, so now we fill out the initial states for P, Q and R. So we've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and lastly 1, 1, 1. Now filling out the not or column, it just reverses from a 0 to a 1 and a 1 to a 0. So you'll have 1, 0, 1, 0, 1, 0. Now filling out the next column, we have P or Q. And P or Q is false only for 0, 0. So if we go to the PQ columns, 0, 0 is the first entry, so it's false there. 0, 0 is the second entry, it's false there. 0, 1, true, 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 and in fact it's true everywhere else. Next column is very straightforward. We take the previous column and we put the not symbol in front of it. So all the values that are here, we just write the opposite, 1, 1, and then 0, 0, 0, 0, 0, and 0. Now let me change colour again for the final column. And what we want to do is we want to take the not or column, which is this one here, and combine it with the not P or Q column here, using this symbol here, which is the if and only if symbol. Now recall again, to generate this truth table, if and only if is false for 1, 0 and 0, 1. So if we point that out, here's 0, 1 as an input, so it's false in that case. Here's 1, 0 as an input, so it's false in that case. Here's 1, 0 again as an input, false. Again, the last one here, 1, 0, it's false. Everywhere else it's true, so basically it's true for 1, 1 and 0, 0. So it's true everywhere else. Now what we do is we compare final columns. And even if you just look at the very first entry of the final column of the left-hand side, that is a 0. And if you look at the entry of the final column for the right-hand side of the logical expression, that is a 1. So obviously the final columns are not the same. So again, if I move down here, I can write at the bottom of the screen that the last columns of the truth tables are not the same, so the statement that was given in the question is not true. That means that the two sides of the statement are not logically equivalent. So new things to remember are, firstly, you need to be able to identify clearly this symbol here that I've put a box around, that symbol is the logically equivalent symbol. And then you need to know what that means. To prove two propositions or compound propositions are logically equivalent or not, what you do is you do out the truth tables for both, and if the last columns are the same, then you conclude they are logically equivalent. If the last columns are not the same, as in this case here, then you conclude they are not logically equivalent. Now let's look at part G. Part G asks, in each of the following pairs of propositions, say if the second proposition is 1 a necessary and 2 a sufficient, or 3 necessary and sufficient conditions for the first. So for part A, the first proposition, I'll write here, this is the first proposition, is I win the lotto. And the second proposition is I have a ticket. Now for part 1, necessary, I ask myself the question, is it necessary that I have a ticket to win the lotto? And of course the answer is yes. So I can write that having a ticket is a necessary condition for winning the lotto. Now for part 2, sufficient. I ask myself the question, is having a ticket sufficient to winning the lottery? And of course the answer to that is no. I would need my numbers obviously to come up. So I write down, having a ticket is a necessary condition for winning the lotto, but is not sufficient. And that's the question answered. Now for part B, proposition 1 is I kill a fly. Proposition 2 is I hit it with a sledgehammer. So for part 1, necessary. So I ask myself the question, to kill a fly, is it necessary to hit it with a sledgehammer? So obviously the answer to that is no. So I write, hitting it with a sledgehammer is not a necessary condition to killing a fly. So to do part 2, sufficient, I ask myself the question, is hitting it with a sledgehammer a sufficient condition to killing a fly? And I would imagine the answer would be yes. So I write down, but it is sufficient. And that's the answer to part B. So doing likewise for part C, I ask myself the question. Now for part C, I ask myself the question, is x equal to 0 a necessary condition for x squared equal to 0? And the answer is yes. And I ask myself the question, is x equal to 0 a sufficient condition for x squared equal to 0? And the answer to that is yes also. So for part C, I find that x equal to 0 is both a necessary and sufficient condition for x squared equal to 0. For part D, I ask myself the question, is it necessary for n to be prime and greater than or equal to 2 for n to be odd? The answer to this question is no. We can just think of one exception to this. If we take n equal to 15, 15 is an odd number, but it's not prime. So I write down, n prime and greater than or equal to 2 is not a necessary condition, so it's not a necessary condition for n odd. The exception, or an exception, being n equal to 15 is not a prime number. Next I ask myself the question, is it sufficient for n to be prime and greater than or equal to 2 for n to be odd? The answer to this is no, it's not sufficient. And the reason, again, just come up with one exception, and the exception is n equal to 2 is not an odd number. So I write down, and it is not sufficient because n equal to 2 is not an odd number. If I move now down to the last two parts of this question. So for part E, I ask myself again two questions. Is it necessary to have 6 numbers chosen to win the lotto? And secondly, is it sufficient that I have 6 numbers chosen that I win the lotto? This is like part A, so the answer would read, I have chosen 6 numbers is a necessary but not a sufficient condition to winning the lottery. And the last part, F, the answer would read, I live in Ireland is a necessary but not a sufficient condition to living in Dublin. Now let me move up the screen here and look at part H of the question. Part H, I'm asked to determine the truth value of each of the following conditional propositions. So the first one says, if the earth is round, then the earth travels around the sun. Now this is an if-then statement. So before I begin, let me remind you of the truth table for the if-then statement. So forming the truth table over here, we have inputs P and Q, and the output P implies Q, or if P then Q. So the initial states are 0, 0, 0, 1, 1, 0, and 1, 1. So let me bring down that piece of the table there, like that. Now, P implies Q is false only in one situation, and that's when the input is 1, 0. So it's false there, and it is true everywhere else. Now let me go back to my original statement. If the earth is round, so let's call this part here, the earth is round, proposition P, and let's call then the earth travels around the sun, let's call that proposition Q. So this English statement then in logic would look P implies Q, or if P then Q. Now if you look at proposition P, the earth is round. That there is a true proposition. It's true, or it has a truth value of 1. If you look at the earth travels around the sun, that's also a true proposition, or it has a truth value 1. So if we go to our truth table, we're interested in this line here. When we have a truth value of 1 for P and 1 for Q, then P implies Q is true. So we'll write that down. P implies Q is true. So the solution is that part 1, that statement up there, is true. So let's do the same for part 2. We'll call if spiders, so spiders have 10 legs, we'll call that proposition P. Rupert has a yellow scarf, we'll call that proposition Q. So in logic, this looks like P implies Q. Now P, spiders have 10 legs, that's false, right? Or it has a truth value 0. Rupert has a yellow scarf. If we presume Rupert is the bear, he does have a yellow scarf. So we'll say this is true. And the truth value is 1. So these two values form the input from my table. So if I look at my table, that's equivalent to this line here. So the output is this value here. So the solution is that P implies Q is true. Or the statement written above for part 2 is true. So the answer is true. So on to part 3. Bonjour is French, is proposition P, and it is true. So it has a truth value of 1. Auf Wiedersehen is Italian. That's a false statement. I'll call it Q, and it's false. Or it has a truth value of 0. So again, if I go to my truth table and identify what particular line this refers to, the first input is true, the second input is false, so overall, P implies Q is false. There's the output there. So part 3, this statement here, is false. Now let me move up the page and do the same for part 4. Again, if I call all odd numbers are prime, proposition P, and I call 15 is prime, proposition Q. Well, all odd numbers are prime is a false statement. And again, just think 15 is an odd number, but it isn't prime. And the statement 15 is prime is also a false. So both of them have truth values of 0. Again, if I go over to the table and I identify the line that this will refer to, the input is 2 zeros, so the output is a 1. So basically, the P implies Q, which is the statement above, is true. That means that the answer to the English statement, if all odd numbers are prime, then P is prime, is that statement there is true. Now if we do exactly the same for part 5, we'll identify all even numbers are divisible by 2 as being proposition P, and all even numbers are divisible by 2, so that's a true statement, or it has a truth value of 1. 8 is an even number, that again is true, and we'll call it proposition Q, and it'll be given a truth value of 1. So if we use this table up here, you can see here it refers to the last line of this table where the inputs are 2 1s. So the output of P implies Q is 1, or it's true. Right? So that means that part 5, that statement that's written there, is true. Beneath this video, you'll find a link to a PDF file which has a copy of the solutions to this logic question, along with tips and things to remember when doing a similar question. I would suggest at this stage that you print this file out. Thank you.